Okay, hello everyone. Welcome. I'm Wendy Liu from the University of Toronto. Thank you for joining us today for the fourth annual virtual conference celebrating the International Day of Women in Statistics and Data Science. This year's theme is Thriving in Your Environment. We are recording this event and the videos will be available on the CWS YouTube channel. We kindly ask you to post your questions to the speakers using the Q&A or the chat. Without further ado, I'm delighted to start our session, S406, Advanced Statistical Methods for Complex Health Data. Before we introduce our speakers, I would like to sincerely thank Stata for their generous sponsorship, which made this event possible. This session features 3 speakers. I don't know if you can see my slides moving down. Am I moving it correctly? Okay, so the session features 3 speakers from Canada, Anastasia, Angela, and Yuqing. They will present their recent work on methodological advances in the analysis of complex health-related data. And our first speaker is Anastasia. So I'm going to unshare. And Anastasia, are you able to share your slides?
Okay.
You are now co-host.
I'm not okay here. I guess I have a share button. I'm not sure actually. I don't see the share option for myself. If I have to do it and share using share button.
You should
I
have
just
a
have
share.
One sharing options. Yeah.
The green box at the bottom. Do you have that?
No.
Green box. Yeah, I do. And when I click on it, oh, here it is. Now I can do it. Thank you.
Perfect.
Thank you. Okay, now it works. Okay.
Yeah.
So can you see my window? The slides?
Yes.
Oh, excellent.
You can make a full screen.
Yes, I'm trying to put it in a full.
Thank you.
Sorry, technical difficulties. I'm trying to put it on a full screen, but okay. I'm very sorry about it. I'm not sure. Maybe I'll reshare. I'm sorry. Sorry. Okay, I'm not sure how this thing works. And then, oh. Okay, I guess I'll have to read it like that. Usually the preview allows me to just, okay, sorry about that. I will just read. Okay, so
try Control L. Somebody told me that one time. I don't know if it'll work.
Doesn't seem to help. So
okay.
I'll just go with like that, okay?
Yeah, that looks fine. No worries.
Thank you. So okay, so the title of my presentation, as my Wendy said, I'm Anastasia Teterina. I'm a PhD student in the University of Toronto. And the title of my presentation is Investigating Temporal Changes in Microbiome Cohort Data using Latent Dirichlet Allocation Approach. So the outline of the presentation, I'll go through the motivating study and research question. I'll talk a little bit about microbiome data. Then I'll describe the 2-stage modeling approach that was used. The first stage was Latent Dirichlet allocation, and the second stage was using features derived in it, and then concluding remarks and future work. So the motivating study was the study in the metabolic dysfunction associated steatotic liver disease. MASLD is the abbreviation. This is the disease that is associated in obesity, quite prevalent. And it has been hypothesized that intestinal microbiome plays a role in its pathogenesis. The research question in the study was, there are specific features in microbiome associated with muscle. So the point here is we were looking not just with like simply different microbiome, we were looking for some features that would be interpretable. So the motivating study was done in a subject undergoing bariatric surgery, which is a weight loss surgery. And most of them have muscle because there is an association. And often muscle is getting resolved after the surgery. There were 61 subjects included in the study. The muscle diagnosis was based on liver histology at 2 time points, baseline and 12 months. And the microbiome samples were also collected pre-intervention and 12 months post-surgery. So the table presents essentially the subject numbers, what happened to the liver diagnosis. 7 of the subjects turned out to be healthy at baseline, so they were healthy in the end. 13 subjects had muscle at baseline, and they still had muscle 12 months post. And majority of subjects, 41, actually had their muscle resolved after the intervention. So a little bit about microbiome data specifics. So the microbiome data set was obtained using it's a result of next generation sequencing process. And this slide presents a brief overview of what the process looks like. This is the very multi-step process of involving extraction of samples. Then the DNA gets chopped into fragments. These fragments get multiplied, then they get their DNA sequences gets read out in a special technology, and then they get reassembled and compared to the sequencing of known organisms. As a result, we get our data set that is essentially has some species with sequencing count numbers associated with the species for each sample. And the point is, at each step of the way, there is a lot of bias and additional variability introduced. So what we see in the eventual data set is not a very precise representation of the original sample. So using some kind of latent variable approaches might be a good option for analysis of such data sets. So in more technical statistical way, the microbiome data analysis is challenging because it's highly dimensional. It's also very zero inflated. Majority of the species variables have majority of zeros in majority of samples. Then the difference in total count between samples prevents the direct comparisons. And the variables distribution in general is non-conforming to any of the distributions that are commonly used for data analysis methods. So therefore, the analysis that we applied here was 2-stage modeling. At the first stage, we used dimensionality reduction using Latent Dirichlet allocation. And then we used the features weights derived in the Latent Dirichlet allocation to model the change in time. Okay, so this slide describes what Latent Dirichlet allocation is. This method was developed in the context of text analysis, where it's called topic models. And the idea is to find in text the words that tend to co-occur in different documents, so they would be called topics. When we talk about the Latent Dirichlet allocation application to microbiome data, we can talk about the sets of species that tend to co-occur in samples in certain proportions, and we can call it latent communities. There is some more technical details about the approach, but the next slide gives the graphical representation of the assumed generative process. So essentially, samples are considered to be mixtures over some latent bacterial communities, and the mixture weights are characterized by vector theta in this schema. Then the latent communities are characterized by distribution over species in their turn, and the generative process assumed for each read count sequencing read goes like this. So first, we sample the latent community assignment for this read count, and then after we know the latent community, a species assignment is sampled from the distribution of the species for this particular latent community. So essentially, what we get in the end of the process is we're going from one multidimensional table to two tables. One of them characterizes the samples in the lower dimensional space of the latent communities, and these are the weights of these latent communities. And the second table is characteristic of the latent communities themselves in terms of species weights. So when we talk about LD application to microbiome data, so the some strong points are that the distributional assumptions of this method is they're conforming to microbiome data characteristics. They're count-based multivariate vectors. They also allow to account for over-dispersion because of the assumption of mixtures of multinomials for each sample. The dimensionality reduction results in biologically interpretable latent variables, which are latent communities. For the implementation in the temporal frameworks, the samples from both time points were included into the same algorithm in this case. And therefore, we assume that the changes in time correspond to changes in proportions of these communities. There was a subjective number of latent communities used in analysis, which was 5. And we can also, additional strong feature, we can apply LD to a subset of variables to examine the role of less prevalent species. And I'll talk about it a bit later. So as a next stage after we derive the weights, they're compositional, so they belong to a simplex. So we can use the Dirichlet regression to investigate if any changes in the proportions of these communities are there, so if they're due to chance or not, essentially. So this is the next slide presents the result of the application of LD to the full motivational data set when all the species are included. So each panel corresponds to one latent communities. There are 5 of them. And as you see, each panel contains just top 10 species and their prevalence, their proportions in the community, the posteriors. So as you can see that the communities are quite distinct. And so therefore they might just be nicely they might correspond to, we can hypothesize the state of ecological equilibrium for the bacteria. So another question was the result driven by highly prevalent species? Highly prevalent means they occur in most samples. And yes, it seems like the community's distinction was driven by the most prevalent species. However, it doesn't mean that the species has to be super prevalent to be kind of a community defining one, because for Latin community 3, this is the top species in each community, and we have more than 50% zero samples for this particular bacteria, and it still is a dominant in one communities. Okay, so in terms of temporal changes, this slide just presents a visualization of the Latin community proportions of the in the samples in each subject. The black lines are the means, and the panels are grouped by the liver status, healthy liver at both time points, liver disease at both time points, and the resolved liver disease. We can see that there is definitely visually, we can see some changes, and they seem to be similar in all groups. So this was tested in Dirichlet regression models, and essentially the likelihood ratio test showed that yes, there is a definite relationship between time and latent communities proportions, but there was no relationship with the muscle status. So this is just more detail of the Latent Dirichlet regression. There are the coefficients for each Latent community and their corresponding well-test p-values. So I'm rushing a bit through this because we started earlier, so we can always come back if there are questions. So there another good feature about using Latent Dirichlet allocation in the microbiome datasets is that we can use it on a subset of species. In general, many of the results of the statistical analysis, especially multivariate analysis in microbiome, they are driven by highly prevalent species. That is, the species have least amount of zeros in the data. Here, actually, LDA is valid on pre-filtered variables. So in this case, I selected 115 species who had at least 50 percent of zeros in their samples, but less than 90%. So of zeros. And when we applied the LDA to this subset of variables, again, we can see that communities were quite distinct. They were, of course, defined by like the dominant species were different ones than if we use it on a full data set. And we still see that there was a time effect when I did the Dirichlet regression on it, and but muscle was not really a factor that is related to these Latin communities. So, and some concluding remarks. So the application of LDA to microbiome dataset allowed to represent samples in lower dimensional space using interpretable derived features. It allows to describe differences in abundance of species and samples while taking into account community structure. So essentially we're dealing with full multivariate vector versus we're dealing with just some separate variables, for example, for each sample. And using features we derived in LD, we can include them in further analysis and see how they're related to clinical variables. And for the future research direction, the immediate work is extending the LDA and application to microbiome data that would allow to take into account time when deriving the communities. So I would like to thank professors from the University of Toronto, Wendy, Michael Escobar, and Naomi Tani for valuable discussions. I'm thankful for Dr. John Allard's research group who provided the data set, and the work was supported by CHR Canada Graduate Scholarship. And there are some references used in this publication. Thank you.
Okay. Thank you, Anastasia. In the interest of time, let's move on to the next presentation. Right. Angela Chang is from University of Alberta, and she is ready to share her slides. Ready?
Yes. Are you able to see my
Okay.
screen? Yeah, is it?
Yes, great.
Yeah,
Thank you.
awesome. Yeah, thank you, Wendy, for the introduction. Today, I will be presenting analysis of zero-truncated recurrent event data by stratified regression with time-varying coefficient. This is joint work with Zhonghu, Rhonda Rosicek, and Lily Zeng. This is an outline of my presentation. I will start with a motivating example, then I will introduce formulation, modeling, and estimation procedure. Next, I will present some results of a real data example. At the end, I will make some final remarks. The Mental Health Related ED Emergency Department, or MHED visit project, is a part of a pediatric mental health care program. The study units were Alberta residents under age 18. They all experienced at least one MHED visit between 2010 and 2017. Available data contains all emergency department or ED records within the time window, and some demographic and geographic information of the study subject, such as sex, the region of residence. This brings us to the central question: how do we learn about MHED visit pattern of Alberta residents under 18 using the available data? For the rest of the presentation, I will refer to the study units as MHED cohort and formulate MHED visits as recurrent events. I would like to use this figure 1 to illustrate populations and samples considered in my presentation. Our target population P is a general population of individuals under age 18. It contains two subpopulations, P1 and P0. Subjects in P1 have at least one event. Subjects in P0 have no events. And the O1 represents the MHED cohort. O1 is a sample of the subpopulation P1, so it cannot be a random sample of our target population. The O0 is a sample of the subpopulation P0. In this context, we address the following two research questions. What are the event patterns in the target population? How does an event occurrence depend on the previous occurrences? The second question motivates us to consider an intensity-based model shown in equation 1. The intensity function tells us the instantaneous probability of having one event at age A, conditional on the event history. Here, we use the age as a timescale. NIA is the total number of events for subject I since birth up to age A. HIA is the event history. SIA denotes the stratification variable defined as a function of the event history. This model depends on the event history only through this stratification variable. Thus, a summary of the event history is sufficient under Model 1. We do not need detailed historical information. Equation 2 shows a simple example of the stratification variable. It means that a subject starts from strata 1 and moves to strata 2 after their first event time. The available data come from subjects in the MHED cohort 01. We have a data extraction window, birth dates, event times. They were all recorded in calendar time. Since we use age as our timescale, then we need to transfer the data extraction window and event times from calendar time into age in years. Thus, we obtain event time in age, AIJ, and the subject-specific window, CLI and CRI. The CLI and CRI are the ages at the beginning and at the end of the data extraction window. CLI is greater than or equal to 0 since no events occurred before birth date. CRI is less than or equal to 18 since we are only interested in events made before age 18. The Q1 and Q0 summarize available information on subjects in O1 and O0 respectively. The Q1 contains all the increments in the counting process within their subject-specific window and co-varies. We know that the increments DIA greater than 0 at least once for those subjects in the cohort. The data are so-called zero-truncated recurrent event data for the target population P. That means we do not observe study units and their observation window until they experience at least one event in a time interval. The Q0 summarizes the fact that all individuals in O0 have no event within CLI and CRI. In our analysis, we made the following assumptions. Individuals in target population are independent. The data extraction window is independent of the events. Birth date is independent of the counting process. Our statistical goal is to use the data to estimate the baseline intensity functions and the regression coefficients. Table 1 shows some relevant model specification. They are the special cases of Model 1. Then we move on to the estimation procedure. I first introduce the idea behind our proposed method. I would like to reuse Figure 1 to highlight what information is available what additional information we need. We let O denotes Alberta residents under age 18 between 2010 and 2017. O1 is the MHED cohort. O0 denotes the individuals without any events within the same time period. And we know the fact all individuals in O0 had no events within CLI and CRI. Then the MHED data, together with the fact, can be framed as doubly censored recurrent event data for target population P, with censoring times and covariates missing for subjects in O0. The doubly censored data are both left and right censored. Only events within left and right censoring time are observed. Population census data summarize the covariates associated with O, including individuals in O0, so we can supplement our primary data with population census information. We consider the local constant estimation to estimate time-varying regression coefficients. The basic idea is that for a fixed A, we approximate beta SU by its Taylor expansion of order 0. For a fixed A, within the interval tau L and tau R, the estimating function for the regression coefficient is shown as follows. The tau L and tau R are predetermined constants selected to avoid the boundary problem. Gamma S is the parameter of interest. Z bar tilde S gamma U is a ratio containing population census information. Equation 4 shows the estimated cumulative baseline function. And we can jointly solve two sets of estimating equations to obtain the estimators for coefficients and baselines. We also establish the asymptotic property and evaluate the finite sample performance of our proposed estimator. In the real data example, there were about 33,000 subjects with over 58 MHED visits during the 7-year time period. Most subjects had 1 or 2 MHED visits. The covariates are indicators for Mayo, Edmonton, and Calgary. Tables 2 and 3 summarize the characteristics of the MHED cohort and Alberta residents under age 18. In the cohort, there were more females and more residents from other regions. In Alberta population, there were more males and more Calgary residents. The differences verify that the cohort is not representative of the Alberta residents under 18. And figure 1 shows estimated regression coefficient for male under the non-stratified model. The blue curve represents the estimated time-varying coefficients. It tells us how the risk of MHED visits change with age for boy compared with girl from the same region. The green line denotes the estimated time-independent coefficient. The right line is line 0, so I will skip the interpretation. Instead, I will interpret the estimation result under the stratified model. The panel A suggests that before age 11.5, boys were more likely to have their first mental health ED visits. After that, girls were more likely to experience their first mental health ED visits compared with boys from the same region. The panel B implied that after the first mental health ED visits, teenage girls were at higher risk of subsequent visits compared with boys. As final remarks, we have made 3 major contributions. We introduced an innovative model. We developed an estimation procedure. Our findings provide valuable practical insights. For the future investigation, we will study how event patterns change across multiple time periods. We plan to extend our analysis to handle multi-type recurrent events. Here are the references of my presentation. Thank you for listening. I would like to take any questions, comments, and suggestions. Thank you.
Okay, great. Angela, I think we should probably continue with the presentation. If there's time, then we can come back for questions. Okay, thank you. All right, so our next speaker is Yuqing Liu. All right, over to you, Yuqing.
Can you see my screen?
Yes.
Okay, hello everyone. Good morning, afternoon, and evening. I'm Yuqing Liu from University of Toronto, and today I'm going to introduce our research on the complete inner-fund trial design in biosimilars drug development. So first, let's start with some backgrounds. The biological products are typically a large, complex molecule used to diagnose, prevent, or treat the disease. However, because of the complexity of the manufacturing and the clinical testing, this kind of drug products usually very expensive due to the high cost of research and development, which limits its accessibility. And that's where the biosimilars come in. A biosimilar is a biological product usually lower cost, while it's highly similar to an approved reference product with no clinical meaningfully difference in terms of safety, purity, or potency. So biosimilars are crucial these days because they can reduce the healthcare cost, improve the patient access, and also promote the competition in the pharmaceutical markets. So to assess the biosimilarity of the candidate product to the original product, so 2 standard randomized study designs are commonly used. One is called a parallel design, and another is the 2-period, 2-sequence crossover designs. So in the parallel design, one group received the reference products, while the another group received the biosimilar candidate products. So this approach is simple, but does not control for the between subject variability because each subject only received a single treatment. So in contrast, a crossover design allows each participant to receive both treatment in separate periods. So, and often there's a washout period between these 2 periods. This means that each subject can serve as their own control, which can reduce the variability and increase the statistical efficiency. So therefore, for the drug with a short half-life, the crossover designs are the preferred choice compared to the parallel design, especially for the chronic disease with the long-term symptoms. And now, before we move further, it's important to talk about one key challenge in the crossover studies called the carryover effects. So the carryover effect is often occur when the residual effects of a previous treatment persist into the next period. For example, in this diagram, after a subject switch from the reference product to the biosimilars or vice versa, part of the previous treatment's influence may still remain even after the washout period. If we ignore or not account for the carryover effect appropriately, we can bias the estimation of the drug effects, and which may increase the rate of we false claim the biosimilars. So additionally, the standard 2x2 crossover design has important limitations when applied to a biosimilar development. So first, it creates for 2 drug comparison, so reference and the candidates. so it cannot compare multiple biosimilars simultaneously. And second, it provides a limited estimation precisions, especially when the within subject variability is large or the carryover effects are present. So this limitation motivates us to exploring the higher order crossover design that can be used for multiple products and also provides the unbiased estimates with the improved precisions. So in this research, our goal is to first extend the standard crossover design for biosimilar assessment from the 2-drug to a multi-drug framework, and also with consideration of the carryover effects. And also we propose a systematic evaluation methodology. And second is to evaluate whether a complete N-of-1 trial design can be used in assessing the biosimilar, and also whether it can outperformance compared to the traditional design in efficiency and robustness. So to achieve these aims, we compare 4 higher order crossover design. So commonly can be used for the multi-drug studies. So first one is called the Latent square design. It ensures each design appear once in each period and in each sequence. Second one is called Williams design. It extends the Latent square design to achieve a pairwise balance across sequences. And third one is used for the reduced number of period called balanced incomplete block designs. It's useful when the full designs are infeasible. And last one is what we're interested in is the complete N-of-1 design. It includes all possible sequences of the multi-drug regimens. So this design are vary in their ability to measure drug effects, carryover effects, and the variability. So for illustration, we're considering the study involving 3 drug A, B, and C, and also administrates over 3 periods. So to evaluate biosimilars, the average bioequivalence approach was used. So the parameter of interest in this approach is the drug contrast, so which is the difference of 2 direct drug effects on the log scale. And instead of testing a single hypothesis, we use 2 separate one-sided tests, TOST, to test 2 hypotheses simultaneously. And only if both non-hypotheses are rejected, the candidate can be considering to have acceptable clinical similar in exposure. The reject criteria of this is the 90% confidence interval of the drug contrast theta, totally fall within the predefined margin, usually is log 80% to log 125%. So now let's look at how we estimate this drug contrast in the hypothesis statistically, while accounting for the design structure and the variabilities. We use a linear mixed effect model with both fixed effect of drug period and carryover effects, and also the random effect for the subject variabilities. So this linear mixed effect model can be written as the matrix formats. The generalized least square estimator of the fixed effect parameters can be obtained by the design matrix and the observation means in the formula like this. For comparing any of 2 drugs, we denote a linear contrast theta, which corresponding to the hypothesis to dedicate the log scale of the drug contrast, and also by defining the coefficient vector of the linear contrast for sequence by periods mean, denoted as omega. The estimator of theta can be obtained by the linear combination of the observation y. So the variance of the theta here provides a direct measure of the precision for the biosimilar comparisons. So for the evaluation criteria and design comparisons, we assume a common residual variance sigma e square and a fixed total sample size written as the uppercase N, under an equal participant per sequence. So especially if both subject variability, if between subject variability sigma s squared is negligible relevant to the within subject variabilities, the variance of the estimated drug contrast can be simplified to the multiply of the contrast weight scalar and the within subject variability sigma e squared divided by the number of the participant per sequence. So since we assume a fixed sigma e squared and a fixed total sample size n, the evaluation matrix would be the BK on the numerators. So it quantifies the structural contribution of each design to estimate third variances. So the optimal design is defined as the design with the smaller BK that indicate the high statistical efficiency and also the small number of sequences, which can improve the feasibility in clinical implement. So here are the design comparison results. We compare the minimum BK across Latent square design, Williams design, balanced incomplete block design, and the complete N-of-1 designs, and are both with and without the carryover effects present. So to identify the design that provide the most efficient drug contrast estimations, we can see that when the carryover effects are present, the complete N-of-1 design yields the smallest BK, indicating the lowest variance and highest efficiency. And in the case of absent for the carryover effects, the Latent square, Williams, and complete N-of-1 trial design all can achieve the same minimum BK. And for the BIBD, the balanced incomplete block designs perform less efficiently in both scenarios. So what does this mean in the practical terms? So under the equal sample size and residual variance assumptions, we find that the complete N-of-1 design consistently provide the lowest variance for estimating the drug contrast across the conditions. Importantly, it remains robust to the carryover effects, where the traditional design such as the Williams design or the Latent square design may lose efficiency. And this suggests it can deliver the greater statistical power for a given sample size, or equivalently, the complete N-of-1 trial design requires a fewer subjects to achieve the same level of precision, even in the presence of the carryover effects. So in short, the complete N-of-1 design offers a unified and statistical efficient framework for the biosimilar development, achieving the precision drug effect estimation and also reduce the sample requirements. And finally, I'd like to thank my supervisors, Dr. Wendy Low and Dr. Shenjong Cho, and also the Teterina School of Public Health in the University of Toronto for their guidance and support on their work. Thanks for listening. Here's the list for the references.
Okay, great. Thank you so much, Yuqing. You make me so happy. We are now ending right on the time that allocated for this session. And Jessica, you must be very proud of me. Okay, so thank you to all the speakers for your insightful presentation, and to you all for joining us for the session. And going to apologize for not able to take any questions at this time. And I hope you enjoy the presentation, and I encourage you to continue to stay on for the remaining sessions of the conference. Okay, I'll see you at the next session.